Okay, welcome back everyone. Today is Monday. We have 2 more weeks to go. We are doing Unit 3B, trusses, frames, and machines. This is quite frankly very tough section. It's not difficult in concept, but you have to be very careful when you try to solve things. You may end up choosing least effective methods, which requires 5 sets of equations. Then you realize, wait a second, this is wrong, and start all over again, kind of thing. It could happen. So I would recommend before you even start solving the problem, you have to kind of observe first and then pick up quickly that how to solve this thing strategically. So I'm going to kind of go back to the past programs and review. Okay. Okay, so class example, we did that in class. So this one, obviously the first thing you need to notice is this is completely symmetric structure, and also force is applied in joint E, which is in the center line. So that means you don't have to solve the whole thing. You can solve 1, 2, 3, 4. That's it. I guess you need 1, 2, 3, 4 internal loading. The other 1, 2, 3 are essentially mirror image. So you don't have to spend time. Okay, well, after B, I'm going to move on to joint C and then joint E kind of thing. You don't have to do such a thing. Okay. Now, obviously, the first thing you have to do here is you need to find out support reactions. Support reactions A, support reactions D. So before you start applying your equations of equilibrium for each joint, you're going to pick up the entire structure and put the support reactions, 2 unknowns at the joint A, AX, AY, 1 unknown at D. You find out those 3 unknown forces first for the entire structure, applying summation of force in X and Y, and also moment at any location set equal to 0. Let's say moment, if you take it at A, of course, those 2 forces does not contribute to create the moment around A. So it is going to give you this support reaction dy as an unknown. This is going to be solved with the one equation. So those are the strategies you need to pick it up and quickly find out dy, and then after that, summation of the force reveals that ax is 0 because this is only force, and then ay is half of it because it's a mirror image. Anyways, that's the first step, and then the rest is starting from joint A. You have ay already known, half p. Those are the 2 unknowns. So each joint, you have 2 equations, practically speaking. This is the method of joints. You cannot apply summation of the moment at this joint set equal to 0. It's not going to solve anything. It is going to produce you 0 equal to 0 equation. So it's meaningless. So method of joints, you only have 2 equations available, force in x and y direction. So it's, as long as you have only 2 unknowns, so those are the 2 unknown, 2 unknown, 1 known force ay, right? So you can solve those 2. Now you have this internal loading known. Using that information, you can solve those 2 unknown. And that's it. You're done. Because this is symmetric. Okay? So that's what I did, I believe. Okay? So I applied the 2 joints. Each set 2 equations. Summation force x, y direction set equal to 0. 2 equations for each joint. Solving 2 unknowns maximum for each joint. So this is the method of joint. Okay? Now, important thing is compression and tension force you have to mention at every loading. In other words, we talked about this. This is actually interesting sketch, yet quite important. Okay, so if you want to know if the member is compressive or tensile, okay, let's say member AB, is this compressive? Ooh, wait a minute. If you look at the joint, FBA is pushing the joint A. Isn't that tensile? I mean, that's how usually I feel. And you too. It's kind of common sense says, well, isn't this tensile? Wait a minute. No. You have to think about that. You have to cut, pick up the virtual cut, and this is portion of the member AB. This is the remaining portion of member AB very close to the joint A, right? So this is the force that you computed. The direction is this way. Isn't this tensile? No, 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 no. You have to introduce equal and opposite at the virtual cut, equal and opposite at the virtual cut. If you take a look at this member AB portion of it, this is clearly compressive force. Compressive internal loading developed. Okay, so this is compressive force. FBA is compressive. Okay, so this is probably the most accurate way to find out, hey, this is compressive tensile. Now, at the point where you apply summation of the force in X and Y direction at joint A, you probably don't have much clue of if this is compressive tensile. So you can assume either direction, that's fine. And then if the result come up with negative value, then you realize, okay, my original assumption of the direction is wrong. Let's flip-flop it, remove the negative sign out. And then you realize, hey, this is compressive. Or you can say FBA is negative, but the direction is this way. Oh, that means FBA is negative, means this is compressive force with the magnitude FBA 0.577 P. Either way, the expression is fine, but as long as you understand what you're trying to say, I'll give you full credit. But please be specific. Direction is going to determine either compressive or tensile, and the magnitude is also associated with it. Go ahead.
Do we have to draw it again?
If you choose to do that, that's fine. I usually try to kind of draw it again. That's why I know, starting from scratch, I know this is direction, because I have a tendency to draw everything again if I got negative sign, because the direction is flip-flop. So I'm going to actually redraw joint A free body diagram and put the correct direction and then remove the negative sign out of it. And then saying, hey, this is compressive. But if you don't have much time for that, for quiz and exam, I would accept if you leave it as a negative, as long as you describe clearly this negative sign means this force is compressive, something like that. If you clearly state it, I'll give you full credit anyways. Okay. It is, of course, nice to have an actual accurate drawing at the very end, but sometimes you don't have time for that. Yeah, go ahead.
So for the method of sections,
Okay.
How do we find if is it the same where it's equal but opposite?
Method of sections. Okay, so again, I hope you did this homework. Okay. Yeah, this homework is probably the same thing. You have to get support reactions first, and then going through joints by joints. Okay. Oh, this is much more work, isn't it? Joint C, joint D, then E and B. At least you need 1, 2, 3, 4 equations. Is that what you did? You needed 4 joints, 2 equations each. Is that what you did? I hope. Any question about this homework? Something you did, right? Okay. Now, I can start from joint A to begin with, because joint A doesn't need support reactions, because those are the 2 unknowns. Using that to find out those 2, using that to find out those 2. The only thing you can never find is this. At that point, you realize, oh my goodness, I needed support reaction. And okay, anyways. So method of joints. Method of joints. One more thing. Okay. Before I move on to method of section. Okay. Method of joints. This is actually a tricky problem. Very tricky. You know why? Why this is so tricky? If I do not cover this as a class example, if I pick this up all of a sudden as a final, probably no one can solve it. Well, I shouldn't say no one, but most of the class probably cannot solve it. What is the problem? Here's a fundamental trick for this problem. This problem is very tricky. Whoever came up with this problem, he knows what is the class issue of method of joints. Now, suppose if your first attempt is, if you think that, okay, the very first step of a truss problem solution is to find out support reactions. You cannot find the support reactions for this case. Do you realize it? You can never find the support reactions. This is a support A, pins. That means two unknowns. This is also pin. Another two unknowns. You only have three equations of equilibrium to find out support reactions. So support reactions A and E, you can never find it. Okay. Suppose if I change this into a roller support, only one support reaction, of course you can find out three unknowns with three equations, but this is not the case. So that's why you have to somehow start from joint C, knowing this is only two unknowns. This is a zero force member. This is equal to that, using this to find out those two. Okay. So that's the only way you can find all the internal forces for this truss. This is tricky. So first of all, you have to realize zero force member to begin with. Okay. And then you need to realize, well, wait a minute, what support reaction? Well, we got four unknowns. So you got to start from point C. Okay. So let's be careful about that. So this one is fairly similar, but this case, this is the support A, two unknowns. This is, I think somebody asked the question, what's this? And then, oh, yeah, Abby did. And then it was a very good question because it actually saved everybody's life. This is actually no two unknowns. This is only one unknown. It's essentially similar to the roller support, only y direction reaction only, Cy. There's no Cx. You cannot support it because it's roller. It just moves. You cannot have a support reaction. It's freely moving. So it ends up being three unknowns. So you can find out Ax, Ay, and Cy, three unknowns, with the three equations of equilibrium of the entire structure to begin with. After that, this is a symmetric. So you only apply maybe two things. Joint A and B. Joint A solves those two. And joint B solves those two. That's it, you're done. And you don't even need to know this. You need to only know this. So it's a very quick solution because this is symmetric beam. I mean, symmetric truss with a force only applied in the center. And then Cy is equal to Ay. Half of P, isn't it? You kind of already know about it, right? Support reactions, half B, because it's symmetric, okay? So again, you can solve very efficiently if you know things. How about this? Oh my. Did you do this? Yeah. This is actually making you think quite a bit. Let me just find out my solution. I hope I did the solution. This is 363. Okay. So I did this solution. It looks like I eliminated zero force members, those two. And after I eliminate those two, you cannot eliminate any of those, even though those are collinear. Wait a minute, this is collinear. Isn't this 0,2?
No.
No. Why not?
It's also like supports thing. Because when I first solved it, I tried to take it as a 0, and
yeah,
it wasn't making sense with the other.
I see. So FFB is what? FFB. Yeah. FBF is, well, 1.864. It's actually a very important member. Huh? So this doesn't, because this is not the three member. This is collinear, but this joint is created by four members. Okay, if this joint F is created by only three members and those two are collinear, of course this is zero force. But this is not the case, yes, right? Good point. So let's be very careful about that. So this being zero force member really means that the joint F is created by only three members and two of them are collinear. The other one is zero. Okay, this is not. And those two are only two members creating joint A, but you are applying support reaction, so you cannot have zero force member. So let's be careful about that. Zero force member detection, two methods, right? Only two members making a joint, and then you have no external force or support reaction applied for that joint. It's a zero force member. if you have three members creating a joint, two of them are collinear, third one is zero force member. Okay, good. So this is the actual structure here. Now, obviously, I can eliminate those two members to begin with. And then the rest is, of course, you're going to find out, first of all, support reactions at E and A. E has two reactions. AY is, of course, this is, what do you call this? This is not roller, but what kind of support? What is the name? Locker or something. Or contact support. I don't know. Anybody remember that name?
Is that the ball and socket one?
It's not ball socket. This is not socketed. It's actually pinned here and then comes with some kind of contact surface on the bottom. So it's like a point contact. And it cannot support X reactions, only Y, because it's free to still move. I don't know what you call it. This is rocker, pinned rocker support or something like that. Okay, I'm not sure about the name, but this one obviously has one support reaction. This is pinned and then connected to the floor. Okay, this is rock down pin, so you have two unknowns. Okay, so obviously you can find out support reactions to begin with three unknowns. So this is the actual structure simplified, and then summation of the force in X, Y, and the moment taken at the pin E set equal to 0, you find out three support reactions to begin with. Then the rest is joint to A, joint to B, joint to F, joint to D to find out everything. It's a lot of work, you know. I don't think you like it, but you have to do it. Okay, so next one is, right? Okay, so the next one is sections. Yeah, so go ahead, your question about method sections.
How do we know, like, if it's tensile or compression for sections, like after it's cut? Is it the same thing where it's like equal but opposite, or is it the actual like?
Yeah, this is all about the discussion of solid mechanics. So we are actually stepping right into beyond statics kind of thing. Solid mechanics is all about internal loading. So always you're going to introduce virtual cut. Okay. So this is a basic example of virtual cut. Suppose this is the original member bar or something. This is obviously by looking at under the tension, right? And you can cut here, virtually cut. Then split this single member into two, right? Then, of course, at the virtual cut segment here, cross section, you're going to introduce equal and opposite force so that if you assemble again, those two forces cancel each other. That's the bottom line. So if you split this single member into two and take a look at each one of them, obviously each one of them is still tension. So that's why this member AB is tension always. Now suppose if you do those two cuts, of course you're going to split into 1, 2, 3 members. Now each one of those members still T and T. The middle member is still T and T because this is equal and opposite, must be. And then T, this is T. This is also T because it must be equal and opposite. When you assemble again, this T and T cancel each other. So that's the internal loading. Okay. And obviously, if you look at any one of those small, tiny members being spread, everything is under tensile in this case. So that's why this member is tensile. Okay. So that's how you sort of introduce virtual cut, take a close look at inside what's happening as an internal loading. Internal loading is all about we are interested because when you have a material try to apply force like this, it's a compressive force. So everywhere internally you have compressive force developed. Okay, and as a result, I'm actually changing the distance here. Internal loading introduces the deformation. Deformation is, in this case, normal stress. So this thing is under the normal stress. Now, how much normal stress do you have? Well, 12 psi. Is it tolerable for this paper material? Yeah, it depends on the shape. What kind of cross section do you have? That is soil mechanics. Okay. So this is one step above statics. Okay. Right. So method of sections, of course, program is typically be asking you, okay, find out internal loading for like some specific members, typically 3 or 2. Then you're going to introduce appropriate cut, expose all of those internal loading. Maximum is 3 though. If you cut like this, you're going to introduce 1, 2, 3, 4, 5, 6 unknowns. It's way too much because you only have 3 equations of equilibrium. You cannot handle that much unknowns. So proper cut is one important thing. So if you want to know every member's internal loading, you probably introduce multiple cut. This cut expose those 3. This cut expose those 3. This cut, well, I don't know. This kind of cut expose those. How about this? What? I don't know. You have to cut appropriately, making it maximum 3 unknowns all the time. Okay. And then after you cut, actually before you cut, oftentimes you're required to find out support reactions to begin with. Okay, before you introducing your cut, you're going to pick up the entire structure, find out the support reactions. In this case, you can find it because this is 2 unknown, this is 1 unknown. Applying 3 equations of equilibrium for the entire structure, you can determine support reactions. Then after that, you're going to introduce cut here. You can find 1, 2, 3 unknowns because you know support reactions, those 2. Something like that. So you have to be aware always how many unknowns are you going to introduce and how many equations in your pocket. It's basically 3 unknowns. And then when you try to apply 3 unknown, 3 equations to solve 3 unknowns, it's always beneficial for you to eliminate one of the unknown or 2 of the unknowns so that single equation including only 1 unknown. In this case, if this is your free body diagram, what is your first choice of the equation to apply for it?
Some of the forces on the x-axis.
Some
On
of
the
the
y-axis.
some of the force in y-axis is okay, correct, because it's going to solve FGC straight up. Or alternatively, you can apply moment taken at point C, eliminating those 2 contributions to the moment. You're going to solve FGF. Or you can set moment set equal to 0 here. It is going to eliminate those 2. You're going to find out FBC. So you can do this. Two moments. Moment 0 here is going to solve this one. Moment set equal to 0 here, solve this one. And then the rest, well, summation of either force of X or Y, finish up this one. Always you have 3 equations about. Okay. All right. So lots of important strategy to make your life much easier. Otherwise, you may end up spending 3 pages of papers and then erase everything, starts all over again. That's actually a common thing to happen. Okay. This is, yeah, we did the class example. We introduced the cut. Before we even cut, we tried to find out support reaction. Then I didn't even care about those 2 because I knew I was going to choose this segment after I cut. So I only needed EY. So I didn't waste my time to find out AX, AY because I'm not going to use it anyway. So I cut it after I found EY out of those entire structure. I found EY as a support reaction. I cut it, picked up this segment, and then applied 3 equations. That's it. So virtual cut method of sections is going to be much, much easier. Usually, you need 1 set of 3 equations to solve everything. If you introduce a really nice cut and strategically apply your equations. This is actually not very good, I realize. I found out FFG first, but after that, I applied the equation of force in X direction, came up with 2 unknowns. Oh my goodness, it's not good. I should have done like a FY first, because summation of the force in Y direction solves you FFC to begin with. Okay, so let's be aware, anytime when you try to solve the problem, if I apply this equation, how many unknowns do I introduce? Or it may end up introducing 2 unknowns for a single equation. Oh my goodness, I don't like it. If so, how about this equation first? Well, this equation gives you only 1 unknown for a single equation. I can solve that straight out. It is going to save a lot of time for you. You don't have to solve simultaneous equation using your cheap calculator. Some of you may not have that kind of function. Do you have that function? Do you have a calculator that actually solves two simultaneous equations with 2 unknowns?
Yeah.
Good. If so, good. But you can actually avoid it, right? By carefully choosing equations. Anyways, this one is fairly simple, isn't it? This one is again support reactions first, either A or G. Cut here, either you pick up this side or that side of cut segment. 3 unknowns, right? Okay. So do you have any question about truss? Oh, this is a symmetric one. Cool. Symmetric means you can actually say this equal to that, this equal to that. Okay. Occasionally, symmetric truss shows up, and then you go like, oh my goodness, today's a lucky day. I'm not sure if I want to choose the symmetric truss for major exam. If I feel happy, I may. If I ended up turning into a huge fight with people, I don't know. I'm a human. Which one do you prefer? Of course, you know. Symmetric truss. My goodness, a teacher is in good mood. Okay. But don't worry about it. You can handle anything. Okay. That's the beauty of engineering. So frames and machines. Okay, frames and machines are again multiple free body diagram. Now each free body diagram you can apply maximum 3 equations, of course. So you can handle up to 3 unknowns for each free body diagram. Now, obviously, if you have a pin support and pin support here, this free body diagram contains 4 unknowns. 1, 2, 3, 4. You can never solve it because you only have up to 3 equations of equilibrium. So you're going to take a look at the other member too. The other member has also 4 unknowns. But those 2 are equal and opposite because you disassembled at the pin B. If you assemble back into pin, those 2 reaction forces need to disappear. So that's why By is equal and opposite. Bx is also equal and opposite at location of pin B. Equal and opposite. This is again, after you assemble, those forces need to cancel each other. That's why. Okay. So ended up having those 2 are not 4 unknowns. This is only 2 unknowns. So 1, 2, 3, 4, 5, 6, total 6. Whoa. I have 6 equations for 2 bodies. I can solve this. Now that's the frames and machines. So let's just take a look at today. Class example 381. Okay. This is a very simple structure. Okay, so I'm going to first of all disassemble those two bodies. Body member AB, member BC. I'm going to disassemble member AB to begin with. Actually, before we do that, I want to find out support reactions. Okay. So support reactions in this case unknowns. Now this is a pin support. Okay. So you are going to have support reaction AX. Now I'm drawing direction to the left. Why? Because I kind of knew the direction to begin with. But if you don't know the direction, you can assume the direction X to the right, and then you may end up having negative value. That means, hey, that's the opposite direction. Okay. Since I know kind of to begin with. So this is AY. 2 support reactions at the pin A, and then C. C is what? C is also pin. my goodness, wait a minute. You cannot do that. You realize, hey, two unknowns here, entire structure. You cannot even find the support reactions. Oh my goodness, forget it. Sorry about that. So, okay. So what should I do? Well, I'm going to disassemble anyways. So member AB. Sorry, lots of erasing. Erasing activity happens for truss and frame programs. Sorry about that. So member AB, I'm going to disassemble. So this is a distributed loading with magnitude 200 Newton per meter. And you have support reaction. This is AY. Then I actually put the AX to the left because I kind of knew the directions to begin with. You can actually put the support reaction AX to the right and then ended up having negative sign. That's fine. Now, FB, okay, what is the angle here?
45.
45, because 3 meters, 3 meters. So rather than two unknowns put in a pin, I want to have support reaction with an angle. This is actually practical sense. This is two unknown because you need to know the direction also. So let's say this is 45, and this is called FB. So this is sort of acting like a support reaction of this member AB itself, okay? Rather than having two support reactions. Okay. Of course, you can choose to go for two support reactions, BA, BY. That's fine too. It's essentially the same thing, but this.
First reason being we needed two support reactions.
Yeah, that's right. So this is the same as that. You can break down FB into two support reactions, BY and BX, right? Okay. You can do that. This is actually beneficial. That's why I'm choosing. So this is the resultant force of 200 Newton meter resultant from A to B, 3 meters. So this is 200 times 3, 600 Newton resultant force. Okay. And the other member. So this is member BC, and then obviously FB. I'm going to put it back equal and opposite. Equal and opposite is quite important because if I assemble joint B, this FB equal and opposite forces disappear, cancel each other, right? So this is FB. Obviously, this is once again angle-wise 45 degrees. Okay. And then here is the C. Okay. This is FC. Now, like I said, FC is essentially two forces. If you break down FC into two components, you're going to probably have this force and that force. Okay. So let's say this is CY, this is CX. Actually, those two forces create FC with a 45 angle here.
How do we know that it's going to be 45?
Because geometry says. Geometry is 3 meters, 3 meters. So reaction force needs to be lined up with this one.
It doesn't mean though that
Hmm?
Cx equals the magnitude of Cy, right?
In this case, must be equal to, because of the geometry. Geometry constrains that components in x and y direction must be equal, because it's 45 degrees of structure need to be supported. Okay. All right. So this actually basically says, hey, you can tell FB equal to FC, isn't it? That's why I wanted to do that. By observation, just making your life simpler. So first of all, let's just take a look at member AB. So I'm going to probably start with some kind of sum of the moment. Let's say this is the positive direction of the moment. Let's sum all the moment at location A. Let's just set equal to 0. Location A is here because AX, AY does not contribute to any moment at location A, only FB. So you can say FB cosine 45 multiplied by 3 meters minus 600 Newton, resultant force multiplied by 1.5 meters. It's halfway through, so this is 1.5 meters. Set equal to 0. So this actually gives you the solution for FB. FB is equal to 424.264 Newton, I believe. Okay. And let's do a summation of the force in x direction set equal to 0. This is going to be minus AX. This is minus because I set purposefully in negative direction of x because I knew this is the direction. If you didn't know, this is going to be positive, but you ended up having negative value for AX, that's fine. Minus AX plus 424.264 sine 45. That's equal to 0. This is going to give you AX straight out. AX is a positive. That means AX is in negative x direction, I assumed. Well, that was correct. 300 Newton. It's sort of semi-cheating because I knew it to begin with. In reality, you probably set up the positive x direction as assumption and having negative value. And then you realize, hey, wait a minute, AX is wrong direction. It's okay, as long as you tell me clearly for that fact, okay? Then lastly, summation of the force in y direction set equal to 0. This is AY plus 424.264 cosine 45 minus 600 is equal to 0. This is going to give you AY, which is again 300 newtons. Okay. So now you move on to member BC. Member BC. Member BC basically says, well, FB is FC, which you know, 424.264 Newton. Okay. Now, if you want to break down two components, in other words, CX and CY, you don't have to, but if you want to break down components, of course, you don't need to, but Cx is equal to Fc sine 45, in which 300 newtons. Cy, Fc cosine 45, in which 300 newtons. All right. Any question here? Go ahead.
I was gonna ask, does it ask us to find whether, or to identify if they're tensile or compressive, or?
This is the determine the horizontal and vertical components of force at pins A and C. So that means you need to have AXAY, CXCY. That's what I think trying to do. So this is a support reactions, not the internal loading for each member. Internal loading for each member, of course, you can possibly find out by partial cut. In other words, if you want to know, that's interesting. Suppose if I cut here, that's not the simple loading, isn't it? Because you have X component and Y component. So if you cut here, what happens is, okay, what happens? If you cut here, suppose this is a cut segment right here. I appreciate your question because this is going to be an introduction for next unit. So if you cut, wow, you are going to introduce perhaps this thing, okay, opposing against Cx, and well, you're going to have this kind of force also at the cut segment, isn't it? Two forces coming up. So let's call this is something called N, normal force. This is a B, shear force. Okay, so as you expose somewhere, you introduce virtual cut means you're going to expose somewhere at the cross section of any member. You're going to expose the internal loading. Internal loading may possibly include force in perpendicular direction, something called shear force. Okay, this is called normal force. May possibly also include the moment also at the cut section. You may end up exposing 3 unknown internal loading: normal force, shear force, and moment. That's probably the next subject, I think. I appreciate your question for that. Okay, so now this is clearly different from trusses. Trusses, if you introduce your internal cut, you only have this force. Why is that? Why is that? Because the trusses are created by two force members. Two force members. Do you remember that? That's the simplification to begin with. Let's just go all the way back and take a look at it. What is a truss? Okay. So truss, here we go. This is important thing. So this is the assumptions for the truss. And then as an assumption, the truss is created by each member of the truss is two force member. That means only the force applied in the direction of each member only. Okay, so either tension or compression, that's it. That's the truss. Now, you're talking about frames and machines. You're actually applying force in the middle. That is actually no longer two force member. If you cut here, you are going to have the force in perpendicular direction also. It could possibly be a moment developed internally. Okay, so that actually making your internal loading a whole lot complicated. You have to figure those things out in solid mechanics. That's the next step to come after statics. Okay, so Let's just take a look at homework here. Homework 381. The compound beam is supported by a rocker at, yeah, that's called rocker, that's right. That was right, rocker. So rocker is pinned to support but the point contact. So the support reaction is only one, By, okay? Wait a minute. A is like a completely fixed supported. So this is going to support X and Y and moment. 3 unknowns shows up here. This is a pin, 2 unknowns. This is rocker, 1 unknown. Total 6 unknowns. So you have to disassemble member AC and CV, come up with 2 free body diagrams. You can apply total 6 equations of equilibrium to solve 6 unknown support reactions. So this homework is actually asking you to find out the reactions of A, 3 unknowns, reaction at C, 2 unknowns, reaction at B, 1 unknown. Total 6 unknowns. You need to assemble those 2 members, introduce 6 support reactions. Okay. Now, once you assemble at C, be careful. At the pin C, support reactions of member AC and member CB, 2 and 2 unknowns comes up. Those are equal and opposite in X and Y directions. So make sure if you assemble at location C, all of those unknowns cancel each other because it's equal and opposite. Okay. This is fairly similar to what we did today. Okay. Let's take a look at the, probably this is the last example of this section. Okay. Class example 382. Determine the horizontal and vertical components of force that the pins at A, B, and C exert on the frame. The cylinder has a mass of 80 kilograms. Once again, this is another discussion. Is this kilogram force or kilogram mass discussion? What do you do? 80 kilograms. Do you take it as a kilogram mass? If so, I think I would convert it to newtons. If you take a kilogram force, you can use it as is, but the kilogram force is inherently non-standard unit. You have to somehow convert it to newton somewhere, so that means, hey, let's convert it to newton, right? How do you convert it? You multiply by 9.81 meter per second square gravity of Earth. This is going to give you Newton value, which is what? 784.8 newtons. That's what this thing is. This is pretty, so this is going to create the equal force of 784.8 newtons. Anyways, right? So I'm going to actually, starting with the virtual cut of this wire, virtual cut of this wire. As you cut the wire virtually, you have a 2 wires shows up. Okay, so this is a pulley. And then here's the rest of the wire. So I just cut and cut. So you know that those are 2 forces, both 784.8 newtons. This one too. 784.8 newtons. So those are all 784.8 newtons. I just introduced virtual cut. Okay. And then I'm going to disassemble member BC to member ACD. So first of all, so member BC is something like this. And then end of member BC, you are going to have a cable which I virtually cut. And then I disassemble at the location C, which is 0.7 meter from the right here. So this is location C. And this is a pin B. You also disassemble. Now you're going to introduce unknowns. Once again, I kind of know the direction of Bx, so I'm going to put the proper direction to begin with, Bx. By, this is support reaction at the pin B. And here, since you disassemble, you're going to introduce two support reactions, Cx and also Cy. And then here, don't forget, this is a tension supporting 780. It's not red because it's known by you. Let me just use a different color, black maybe. So this is a known force, 784.8 newtons. Okay. All right. So this is the free body diagram for member BC to begin with. Now,
BC or B speed?
You're talking about what?
Yeah, you take all of it, right? You don't look until C.
Yeah, I disassemble pin here. That's location C. This is a pin anyway, so you have two support reactions, right? And this is also pin, so two support reactions. And here I just cut. Cut and expose internal loading of this cable. Okay. I hope this is correct. Yeah, I think so. And let's draw another free body diagram for the other member, ACD. So ACD, I'm going to, all right, disassemble pin A. So this is going to be member ACD. Okay. And right here, by the end of this member, you have a pulley. I'm not going to disassemble this pulley. I just keep it as is. But I'm going to cut, like I said, cut the wire here. So the wire is coming down here. Wire is coming down here. The other side also. I just cut. Okay. Then replace with known value of force, in which each of them is 784.8 Newton, 784.8 Newton, each of them, okay? That's the pulley. And around here is pin C. Once again, I'm going to disassemble. Now, as I try to put unknown forces here, I try to make sure this is equal and opposite because this is different member. So if I set Cx positive right, I'm going to set Cx positive left. It's equal and opposite because I disassembled it. So this is, here is Cx, equal and opposite direction for this Cx. And then here, Cy, equal and opposite for this pin, Cy. So if you assemble that, those Cx and Cy disappear. So as a result, those are actually not the four unknowns, but only two unknowns. Okay, Cx and Cy. And here's a pin. Okay. So this is Ax. This is Ay. So you have two free body diagrams, and then take a look at each one of them. Okay, so I'm going to start with, by the way, wait a minute. Do we know the distance here? Just a note. This is a 0. What's the Do we know the size of this? I don't know. Do I know the size of it? Well, I have to give you a size, isn't it? Yeah, size is missing. So let me just add, okay, note, this information is necessary. Let's just create this dimension. Diameter of pulley is, let's say, 0.2 meter. Let's just add that additional information which is missing. You need that to solve this problem. Okay, so this is 0.2. Let's just add. Okay. Okay, sorry, the program has some issues. Please add this information to your original program statement. If I create this as a quiz or exam, I'm going to add this information to the original program statement. So let's just take a look at member BC. Okay, so this member. So I'm going to, of course, I can apply like 3 equations. First of all, let's just apply. This is the summation of the moment. This is a positive direction. Let's just add this to B. So this is summation of all the moment at location B must be equal to 0. Why did I choose B? Because I wanted to eliminate BX, BY, and CX doesn't contribute any moment to position B. So you only introduce CY, isn't it? Okay. So that's what I wanted to say. This 784.8 Newton create the positive moment. 784.8 Newton multiplied by the entire distance. Entire distance is what? 1.7 meter, right? 1.7 meter positive, okay. And then CY creates negative moment. It's negative CY times the distance is 1 meter measured from B. This must be equal to 0. This is going to give you CY, which is equal to 1,334.16 Newton. Okay. The next is summation of the force in x direction set equal to 0. Okay, so this is going to be negative bx plus cx is equal to 0. Oops, this is 2 unknowns. So this is going to say bx is equal to cx. Let's call this equation 1. Okay. Summation of the force in y direction set equal to 0. This is going to be by minus cy, which is, we know, 1,334.16 Newton, plus 784.8 Newton set equal to 0. This is going to give you by. By is equal to okay. So we still don't know cx and bx. Okay. By is 549.36 Newton. I hope those are all correct. Okay. So one thing we still don't know is what's bx and what's cx. We still don't know. 2 unknowns still remains here. Too bad, because we have 4 unknowns total. We only have 3 equations. We cannot solve everything. Now, go ahead.
Can you find that angle at C? Because it's a right triangle. And solve.
You're talking about this angle?
Yeah, that angle at C. Is that 0.5 and 1 means a right triangle?
Yeah, you can find out because this is 0.5, 1 meter, so you can get angle here. Yeah, that's right.
Couldn't we also take the moment at C to find, oh, never mind. That you wouldn't find it.
That actually gives you probably redundant information of the other two. Yeah, okay. So yeah, we can find angle, however, that actually introduces a new unknown here, internal loading, which we don't want to introduce. Another unknown shows up. Okay, so anyways, so this is pretty much we can do for member BC. We solved the CY, BY, but we still don't know BX and CX. The problems being we have 4 unknowns to deal with. We only have 3 equations available. Okay, so I'm going to move on to the other member. The other member hopefully provides additional information. Member ACD. Okay. Okay. So member ACD. Let me just zoom out a little bit. Okay. Member ACD, this thing. So again, we have 3 equations. I want to start with probably the moment at either A or C to eliminate. Since we want to know maybe CX to begin with, I want to probably start with moment taken at the location A. So sum of the moment, this is a positive direction moment. Summation of the moment taken at location A set equal to 0. Okay, so this actually eliminates AX, AY contribution to the moment. CX and CY produces the moments. Okay, so first of all, CX multiplied by this distance. This distance is, what's this distance? Do we know that? From here to here. 0.5, that's right, we know that. So Cx times 0.5 meter, positive moment, plus, okay, plus Cy, do we know? Yeah, we know Cy. So Cy is 1,334.16 Newton, that's Cy. Cy times this distance. We know this is 0.5 meter. What's this? This is 1 meter. Here we go. So this is Cy, which is 1,334.16 Newton times 1 meter. And this is going to be a positive moment. And those 2 forces create negative. So this is 2 times, not the 2 times, I shouldn't do that. Okay, so negative first moment, 784.8 Newton times this much distance is 1.7, right? 1.7 meter minus another 784.8 times this one is 1.7 times 0.2, 1.9 meter. Set equal to 0. So basically 4 forces creating moments around point A. These 2 and these 2. This force create negative moment. This also create negative moment. Okay. By solving this, you can get Cx out. Cx is equal to 2,982.24 newtons. Okay. Next step is, well, it's getting closer. Summation of the force in x direction set equal to 0. This is x positive direction. You're going to get AX minus CX is equal to 0. This is actually meaning AX equal to CX. And then, do we know one of them? CX, we know it. So this is the same as CX, 2982.24 newtons. Well, AX is equal to CX. Summation of the force in y direction set equal to 0. This is going to give you AY plus CY. CY is what? CY. Well, we know CY here, 1,334.16 Newton. And then 2 of those, negative direction, minus 2 of 784.8 newtons. Set equal to 0. And from here, you can get AY. AY is equal to 235.44 newtons. Then one thing remains. That's just to pick up equation 1 all the way. Okay, so this equation all the way. Let's just pick it up here. Okay, so from 1, you can say Bx equal to Cx. Cx we know. So Bx is equal to Cx, which is 2,982.24 newtons. All right. Solution seems to be simple if I do it in class, but this may take 1 hour to do. I don't know. So again, you have to budget yourself. It's not difficult thing, but you have to. Okay, there's certain things you have to be very careful. First of all, free body diagram, of course. If you do a wrong free body diagram, that's it. You can never solve it. Okay, so carefully disassemble and make it free body diagram. You don't have to make a beautiful diagram, but you have to make it accurate as you can do. And then put all the unknowns. Of course, you probably don't know some of the unknowns. You don't know the direction to begin with. You just assume a positive direction. If so, then you may end up having negative sign. That means you know the direction is opposite from the original assumption. Okay. And then don't forget your external loading. External loading must be all shown to these two free body diagrams. And clearly apply each free body diagram. You can have up to 3 equations of equilibrium. Okay, up to 3. So that means only 3 unknowns you can handle for each body. So you may end up having left off, okay, Bx and Cx we never know. Of course, you have 4 unknowns for this free body diagram for member BC. So you need to keep it kind of leaving for a moment and then move on to the other member, trying to solve the unknown forces, and some of them are equal and opposite. You can determine everything. Okay, so this is probably one step further than truss problems. You have to disassemble for multiple bodies, and each body you're going to apply 3 equations maximum for 3 unknowns. Okay, this is basically 2 members, but sometimes you have to disassemble into 3 members. That's what this thing is. No, this is still 2 members. Yeah, well, suppose if you introduce like a 3 members assembled up, those are the machines, you have to disassemble. You now have 3 free body diagrams, each can have up to 3 unknowns. So you can solve total 9 unknown forces and moments for those machines. But again, everything is basically same principle, same strategy. But if you do a wrong thing, I guess you get stuck and you can never solve it. It takes hours and hours you spend, and you bang your head up over the wall and then say, well, erase everything, start all over again. That actually happens. It's a normal thing. I did that. I went through that when I took this class. Okay, so this is actually statics. Statics is I think engineering mindset builders. you're going to experience. This is all about engineering. If you're going to be an aerospace engineer, this is going to be like your first job assignment. Can you handle that? Of course, you should be. So I'm acting like a big nasty boss in your first employment. You need to satisfy me if you want to pass this class. Okay. Any question? This is the end of 3B. So we're going to stop here today. So tomorrow is Tuesday. It's all online. Yeah, go ahead. Question.
Do we have a quiz today?
Do we have a quiz today? I think.
We did. 3A.
Oh, that's a great question. We don't have time for that, right? So what should I do? I didn't realize. Wait a minute. Did I set the?
Switch it back to.
Didn't I set the timer? I forgot to set the timer. Oh, I was too upset this morning. That's why. Everything is those people's fault. So, yeah, any suggestion?
Since the 3B quiz is going to be on Thursday, we'll just do it on 3A on Wednesday.
Do you want to do that?
Yes.
No, let's just do it.
Okay.
Oh, yeah.
Let's just do it now?
No.
No. Because you got only like 7 minutes. I don't think you can do it.
Wednesday?
Wednesday? Two quizzes in 2 days in a row. If you have a complaint, please speak up. I mean, you can. Oh no, you have to think twice. Okay, if I push back this one there, what happens later? You got to do it anyways. So, so consensus is what? Do quiz on Wednesday. That's 3A. Then Thursday is 3B. Yeah. Oh yeah. Can you do it? Okay. If you know it, you can prepare for it, I think. All right. Okay, so far, okay? Okay, everyone? All right, have a wonderful day. Let's plan for 2 quizzes Wednesday, Thursday. All right, have a good day.